Hello, everybody. Thank you so much for being here today at our team's proposal for improvement in urban air mobility. Today, we'll be discussing our company's design and comparing it to other competition to show you why you should invest in CLS, the Civilian and Load System Company. I'm Savannah Scott, and I'm a fourth year aerospace major at Georgia Tech.
I'm Carlos Mercado, and I'm a fourth year aerospace major at Georgia Tech.
And I'm Leanne Manuel, and I'm a second year, and I'm a aerospace engineering major at Georgia Tech. So picture this, it's a Friday afternoon and you're done with work and ready to head home. You happily leave your office, only for a thunderstorm to roll in, resulting in even more traffic than usual. The commute for you and so many people becomes full of stress. But here comes our solution, the Orca Air. This fully electric urban air mobility vehicle is designed to serve as a new taxi service and solution to the ever-growing traffic problem. And within the UAM field, our aircraft solves the problem of a lack of weather protection in current designs.
Our mission as a company is to provide safe and reliable air transportation throughout cities across the U.S. To start, however, we're just implementing our system into Dallas, Texas. In order to achieve our mission, we're designing an urban air mobility vehicle, or UAM vehicle, that's able to safely perform in the typical weather conditions of Dallas, but in the future, it should be able to function for any urban city. These conditions could range from small precipitation to strong winds and snow. By creating such a vehicle, we are able to offer our services to a broader market, improve public transportation, and even reduce air pollution. We believe urban air mobility as a whole would become more prolific if the vehicles could successfully function in urban temperatures and weather conditions of the environment, as well as to provide comfort for the passengers. Improving urban air mobility would improve public transportation, which would help develop infrastructure and lower pollution in general, as roads would become less congested.
Now, how are we going to implement this service into the cities? First, we'll start by building a ground control station that is able to talk to the Orca Air to give it important information such as when to charge and what the current weather patterns are in the area. This ground station facility will include both the technology and personnel for weather monitoring and for UAM air traffic control, since the UAM vehicles will have their own airspace. Then we'll use a combination of current helicopter pads as well as our own launch structures to implement a bus station-like service into the city. Part of the ground facility's role will be to monitor each vehicle's location and to determine when each one should take off and land. The ground station will also have the capability to tell if the passengers are safely in place before takeoff.
This N-squared diagram shows further detail about how our interfaces will interact in our proposed system. This section displays some of the inner subsystems of the vehicle, and the navigation interface includes the LiDAR remote sensing system on each vehicle, decreasing complexity. On the next slide, we can see how the vehicle will interact with ground control and weather monitoring systems. Although these two components would be in the same facility, nearer inside the city. An aspect included in the weather monitoring interface is the LiDAR devices installed in the city, which will allow for redundancy in navigating the UAM airspace and mainly investigation of the wind fields and turbulence.
Our top-level requirements for the vehicle included being weather tolerant, providing safety for the passengers, being able to communicate with the navigation system, providing comfort to the passengers, and using clean energy for power. We also had requirements for a ground station, such as gathering and sending weather information to the vehicle, overseeing the loading and unloading of passengers, deciding when the vehicle should charge, and having control of the takeoff and landing.
We looked at the designs of other companies to gain insight on some of the fundamental architecture of modern UAM vehicles. We saw that many of the top companies were using multi-rotor configurations as the main lift generating mechanism. Also, most were going with clean energy power sources using either fully electric or hydrogen fuel cells. Some companies are also working toward autonomous flight capabilities for the future, but they also include pilot control for flight operations.
When looking for inspiration for the design of our vehicle, our team didn't just copy other prototypes. We started with looking at some of the baseline aero vehicles and generating a pros and cons list for each type. We then analyzed these pros and cons and designed the Orca Air around the pros while trying to improve upon the cons.
For our design architecture options, we considered some of the most popular lift generating mechanisms that consist of single rotor, multi-rotor, fixed wing, or hybrid wing combinations. Other major options for our design were between fully electric or combustion engines for the powertrain, and deciding between piloted or fully autonomous flight control. We also considered weather-resistant capabilities for lightning, ice, heavy winds, and flight in little to no visibility. Other architecture options such as communication capabilities, vehicle safety features, and passenger comfort were for the most part predetermined by federal requirements, our mission requirements, and industry standards. We performed a preliminary trade study to compare performance parameters between some of the top companies. This was a mainly qualitative study where we placed weights on the different evaluation criteria based on what we felt would best help us meet our system requirements. Since our main focus is being able to transport passengers between relatively short distances in urban areas, we placed the highest weights on maximizing passenger capacity while also minimizing noise levels and cost. For our design, we went with multiple rotors to maximize vertical lift and minimize noise levels. This would allow us to operate in tight places without needing a runway and allow us to operate at noise levels that do not disturb the city's residents. We also included a fixed wing to utilize the natural lift force it generates. This allows the vehicle to carry a similar weight to a purely multi-rotor vehicle while also reducing the power required to maintain lift during cruise conditions. We went with a fully electric powertrain to minimize pollution since the technology is available and it has proved it's capable to perform these operations. We also have to take into account obstacle detection and avoidance, optimal flight paths and air traffic control, and operation during different weather conditions. The urban landscape presents many more rapidly changing variables than those compared to longer range flights with human pilots. We believe fully autonomous flight can make the optimal decisions needed to operate safely in this environment. Additionally, we will include weather-resistant capabilities for lightning, icy, and windy conditions. We believe this will be a main factor in allowing urban air mobility to open a new market for passenger transportation. We want to be able to continue safe operations during these conditions, similar to how ground-based transport can continue to operate in the same conditions.
Here's some more details about the design and its functions. LiDAR, or light detection and ranging, is a method of remote sensing that will have multiple uses in our architecture. Each UAM will be equipped with LiDAR sensing, which will allow for 3D visualization, altitude sensing, and autonomous navigation overall. If the vehicle is piloted, LiDAR will still be used for conditions in fog and rain, or low visibility. LiDAR scanners have also been tested to identify wind directions and turbulence. So the devices will be installed in the city, which will allow for the creation of wind models for the Orca Airs to use to avoid large wind changes. Regarding the other weather protection, the vehicle will utilize developing ice-phobic coating researched by individuals at organizations like Airbus and Carleton University. The coating protects against ice accumulation and actively defrost material, providing extra protection. And the vehicle will be composed of an aluminum alloy and partly with composite material like fiberglass, decreasing weight for more efficient flight, but also compromising so the cost is less expensive. The windshield will also use the design of Storm Shield Aeronautics, which can withstand a load 8 times greater than competing manufacturers, protecting against hail and large objects. To protect against lightning, conductive coatings can be used, replacing traditional metal mesh lightning strike solutions. And as discussed previously, our design includes fixed wing and 8 tilting rotors for a hybrid design, optimizing the space and time required for takeoff, landing, and cruising. To provide comfort for civilians, the rotors will be coaxial and co-rotating, which significantly reduces noise, as tested by the U.S. Army and other groups.
By 2025, we expect a manufacturing cost of $400,000 per vehicle with an annual maintenance cost of $9,000 per vehicle. Our total cost of operations for the year is expected to be $4.5 million. This includes the cost to run the ground control stations and the vertiport facilities. We expect a revenue of $2.5 million per vehicle that will come mostly from the sales of the vehicles to other companies. We will also gain revenue from passenger fares of $4.50 per passenger per mile. By 2027, we expect profits of $1.5 million per vehicle as our vehicle production rates increase, our production costs decrease, and as more passengers use our services as the technology becomes widely accepted by the public.
This year, we've already entered the design and research phase. By 2022, we will begin developing our subsystems and start building the prototype. At the end of 2023 and beginning of 2024, we will enter the testing phase and have our first passenger flights occur. And by 2025, we will be ready to enter the market. In conclusion, the CLS Urban Air Mobility Vehicle, the Orca Air, is the best choice for your investment. We have made a zero-emission vehicle to decrease pollution.
We prioritize the safety and convenience for flyers and cargo by emphasizing protection from weather and utilizing quieter propulsion.
And we focused on the details of implementing our transportation system into cities to decrease costs and provide a successful aerial option for civilians. We look forward to hearing back from you. Thank you for your time.